before we move on, let's you can see clear. Okay, let's recap what is chapter 6 focus. Chapter 6 is on mechanical properties, which is on loading of a project on an object. Load can be pressure, can be force, can be stress. Okay, depend on the direction of the forces or pressure or stresses. You have tensile loading, you have compressive loading or compression loading. You have normal something, you have shear something. Okay, it can be normal force, normal stress, it can be shear force, it can be shear stress. For stress is equal to force divided by area. For strain, strain is the deformation. Something change, the shape change. So you're calculating the ratio. If the question asks you strain, it can be change of length, change of length to the original length. It depends on two directions. One is longitudinal, one is lateral. Longitudinal is along the axis. Lateral is on the side, on the side of the axis. Okay. Then here we learn about Hooke's law. If you stress equal to capital E strain, this one is modulus of elasticity or modulus of Young. Strain, you have two. Strain, it can be lateral. So when the strain, longitudinal lateral give you Poisson ratio. Poisson ratio equal to what divided by what? Longitudinal or lateral? Which one? Can you refer to your notes? What is a Poisson ratio? Poisson ratio is what divided by what? Lat divided by long. This is a negative value if it is a tensile loading. If it is a compressive, then this one become positive. Okay, because when you pull, deformation will change from the on the lateral side. Okay, if tensile loading, lateral will be negative. You want to get positive value for Poisson ratio, that's why you put a negative there. Right, longitudinal, if you pull both end, tensile loading, strain, longitudinal will be positive. If it compressive, lateral will expand. So you'll get a positive value. Okay, positive, then longitudinal will be positive. So you get a positive value of Poisson ratio. Okay, so remember our Poisson ratio, the negative sign only apply for tensile loading scenario. Mean you're pulling both ends scenario. Only you apply the negative symbol. Yes. Okay, because we want to, our Poisson ratio always positive value. So when you in the tensile, what happened to your lateral direction is string, right? The middle part string, the area string. So the lateral will be negative value. So you negative, you get positive value. Then the longitudinal, always positive. The value always positive. So that's why tensile loading, when the tensile condition, you only apply Poisson ratio equal to negative. Then strain let divided by strain longitudinal. However, compressive, you don't go and use negative. Compressive, you don't need negative. Or you just remember Poisson ratio always is a positive value. Okay. Uh, reduce in area, in dimension of the lateral direction. Yeah, correct. So, yeah, correction. Longitudinal, if it's compressive, it will be negative, correct. So we still need the negative. Okay. But anyway, Poisson ratio always get positive value lah. Okay. Okay, Hooke's law. After we done Hooke's law, there's an equation that link your stress with 2Vg plus 1, no, 2G Poisson ratio plus 1. This one to link the stress and strain. Check this one. I forget the formula. Okay. What's the equation that link your G with the stress? Is it correct? Stress equal to 2G bracket V plus 1. Is it correct? Correct, right? Something missing? E. In front is E, right? Okay. E equal to 2G bracket V plus 1. This one come out last semester, that asks you to find the elongation with the G, with the Poisson ratio. Okay, so Hooke's law done. Then on the diagram, stress versus strain. So you should know how to read the graph by now. So there is an elastic region that give you modulus of elasticity E. It is this line, straight line. Okay, and from here to find yield stress, you need the analysis of 0.2% analysis, where of not Poisson ratio, the strain value of 2%, 0.2% will be here, 0.002. So then you draw a parallel line, you will get intersect with one point here, move to the left, you'll get U point. Then stress max or stress UTS, ultimate tensile strength, which is the maximum point on the curve. It's this point. This one will give you UTS, stress UTS. You go to the maximum point. Then, of course, fail point will be the point of graph, or fracture point or fail point graph. Okay, then from the graph, you can calculate the resilient modulus of resilient that what you see on the screen is the area under the graph in the U section. In the U section, in this case, if you see this graph on the screen, y-axis is stress, x-axis is strain. So we are looking at the U point. So remember, when you calculate the U point, you need to do 0.2 analysis to find the U point. So you pull out, find the U point. Basically, it's a triangular shape. Half base multiplied by the height. Okay, the base will be the U stress, U strain multiplied by the U strain. Unit will be Newton meter over meter cube or Newton over meter square or Joule over meter cube. So this will be we stopped at here in the previous lecture. Okay, so this is just amplified the highlighted area. It amplified. So remember, to find the modulus of residence, you need the U value for strain and stress. To find the U value, you need the 2%, in this case 2%, 0.002 is a 0.02% analysis. So you draw a parallel line, you get the point, and then extend to the left. So if you're given a graph, please show this dotted line for the 2% analysis on the graph. Okay, then extend to the left. When you see one value, please write the value that you see on the graph. Then in your calculation, you substitute back the value on here. Okay, or in other case, you can just straight away use the modulus elasticity and the yield stress value, because strain equal to stress divided by E by using Hooke's law. Hooke's equal to stress equal to modulus Young E and the strain. So this strain, yield strain, you can modify it become stress divided by E. So you have half yield stress square divided by E. If you are given a table, only have a U value and the modulus Young. Okay. Next, we learn something new for this morning. If toughness is area under the full stress strain curve, which is you find from the 0 until it fail point, like one you see on the screen here. So here you actually consist of a few shape. Hope you can see. One, we break into the rectangular shape. Then there's a triangular shape, and there is a minor area over here. Okay, you can use a trapezium analysis if you want, using computer, but this one you just need to calculate a trapezium shape, which is a rectangular plus triangular, and this one is a minor area. If you want to find, you can find if you're given the equation of this parabola. You just integrate from this point to this point, or this point to this point. It depends on the equation given. So this one you cannot see the red color. Okay, just exercise using the same graph. Given the engineering stress diagram, here engineering also means normal stress and normal strain. Engineering also means normal stress, normal strain. Please find the modulus of residence and toughness of the material. Okay, means you find area under the graph. UR, you need to find the U point on this graph. So, the graph is a bit small, but if you download from the tutorial question, you should be able to find. So, if you see the graph on the left, the U point will arrive at okay, this one is in PSI. If you extend to the left, is in megapascal. Okay. So I'll just show you the value. So if you extend to the left, you'll get around 530 megapascal. And if you download the tutorial graph, you should be able to see the value. You can estimate. You can estimate error will be 10% from the graph. So let's say this. Take this example. The yield stress will be 530 megapascal from the graph. And in your calculation, if you give me 550, you get the wrong answer. Okay. The line, if I intersect this line over here, the maximum I will not accept 550. 550 too much already. Okay. If your answer is 540, I still give you correct. But if you give me more than 540 means too much already. You read the wrong graph. Okay, I'll give you the value. And the yield strain will be 0.008. Just estimate from the graph. Of course, in the exam, the graph will be full A4 paper. You'll be very clear on the point. So from these 2 points, already give you 2 points. You should use your calculator, find the modulus of residuum. By seeing these 2 points, you should be able to find the modulus of residuum by half base and the height of the triangular. So what is the answer from your calculator? Modulus of residuums. What's your calculator tell you? And tell me the unit. What is the unit? So what's the answer? Right in your answer, you are equal to half stress U and strain U. So here, since modulus Young is not given, of course you can find if you want, but straight away from the graph you find 2 value, 530 megapascal, or if you scared you forget 10 power 6 here. Stress will be 0.008. So what answer you get? 2.12. 10 power 6. What's the unit? Huh? Okay. So you can put in Pascal if you want. So 1.2 megapascal. Because this one is megapascal. This one dimensionless. So you still get megapascal at the end. Okay. 1.12 megapascal. Or you just put in the index form. 10 power 6 Pascal. Okay. So yeah. Is area under the elastic line, a yield point. Or how you apply this one, right? Your question is, okay, so actually is application is more on the, okay, want to show you the unit. Okay, the unit can be joule over meter square. So if you want to press the object or press the material, you can set how many joule of energy to make the metal to deform as a meter cube in 1 meter cube. So you want to press the things, you can measure in, you can design your energy of pressing in joule, or you can put in Newton meter. This is work done on the meter cube. And this one is Newton over meter cube, means you are pressing the material area with how many newtons. So it's like if a piece of piece of metal sheet, you want to roll it become a thinner. So you are applying the how many Newton on the surface of area, so that this one can deform, or you can even make comparison between metal 1 and metal 2 also. Like you fix the Newton, and then you see which one is more easier to deform. Okay, application for modulus of resilience is more on the material selection for the engineering design. Modular toughness is toughness is the whole graph under the thing. This one is to find a quick comparison between metal to metal. If you have a certain amount of pressure on that. So you just want to do a quick definition. For example, you design a propeller for a ship that work under submarine application. So you can compare titanium and normal aluminum steel for the propeller under maybe 1,000 feet or 1,000 meter below the sea level. So you want to see whether it can maintain or not that shape under that pressure. Okay. So this one you can use a trapezium method or any method. So it's under the graph. All the area under the graph would be around 46 megapascal. Okay. Okay. So example 9, it's good that you can download the tutorial question. Chapter 6. Chapter 6 tutorial question. You see a graph there. So the ask you from this graph is ask you to find modulus of elasticity, yield strength offset at 0.002. Of course, in the test, we won't be this direct. We will tell you calculate the yield strength at 2%, 0.2%. So you need to find the value of this one. The maximum load that can be sustained by a cylindrical specimen. So basically, you're given diameter. And changes of length of specimen original, so much long and subject to tensile stress, so much long. So you find the change. So you're given this diagram. Okay, this diagram is the tensile graph with this stress and strain. Okay, stress and strain, and the enlarged portion in the middle for the elastic region. Okay, elastic region, you have even it give you the yield strength already in the graph with 0.02%. It extend to give you the value of 250 megapascal yield strength. Okay. Modulus of elasticity, call out, you write Hooke's law, you write you write stress equal to E strain. And from the graph, this is your Y, this is your X. So basically, E is the gradient, your M, where you take changes of delta stress over delta strain. Okay, means y2 minus y1, x2 minus x1 in the calculation for gradient M in the graph. So here, you can pick any point on the graph. Just need to read carefully the axis. In the middle here, you have megapascal and PSI. Don't read the PSI, read the megapascal. Okay, so here, you read the 200 megapascal graph axis. You read 200, you use a ruler, you will touch one line on the curve, expand down, you will get one value here. So let's say I take 200 megapascal just to get a full number. I expand to the left here. I move down, is about 0.2. I move here. maybe I don't have a straight line, so maybe 0.2, roughly lah, roughly 0.2. Okay, so you move down will be 0.02, will be about 0.02. Okay, so you have 0 point here. This is delta x. Here is delta y. Substitute value there. You take 200 megapascal divided by 0.02, you get your modulus Young. Put in gigapascal normally for metal. Okay, press your calculator, you get the numbers. Okay, this one is more larger. So it's more larger. You can see the graph. So 200 expand here, move down about 0.2. So I just pick, in this one, I pick 150, but you pick 200 is better lah. This is a bad example. So 200 move down is about 0.2, 0.02. Right? 0.02. If you put 200, you get around 0.002. If here you get around 0.015. Your answer will be around 100 gigapascal. Okay, the answer for the first section will be 100 gigapascal. Okay, second one. And from here, so this question extend, then you'll see one table in the question. From this one, pick anyone, any member, estimate what is this graph belong to which metal alloy. So E is this one, 100. It can be brass, it can be copper, it can be titanium. Based on the estimate answer, it can be brass, it can be copper, it can be titanium. So your test one and final exam question will be like this direction, on this direction. So once you calculate one answer, you need to refer to table, estimate what is that material. Okay, so if you don't know what I'm asking, then you need to repeat. Go and see example 9. This is important. Lots of question will be in this kind of question. Once you get answer, you need to tell me what is, so what. Once you get the answer, then so what. Usually it's selection of material. You get one value, then selection of material. So just don't read the wrong column. You have modulus of elasticity, you have shear modulus, you have Poisson ratio. Okay. So it could be brass, the closest one. It could be brass because it's only difference of 3 Pascal, the closest one. But your answer can be estimate 3 types. So if you see the question, read carefully. The question, sometimes the wording, estimate, estimate or predict the type of material. If you only see singular, means one material. If you see materials, then it's 3 answer. Read carefully. Sometime without S, sometime with S. If material, then it's 1 material. If materials, then choose 3 the closest, or maybe 2 the closest. Okay. In this case, we choose brass, right? In this case, we choose brass. Or sometimes the question asks you the closest, predict the closest material for this chart. The closest means one type of material. Okay. Yield strength 2%. So if you look at this one, already give you the yield strength from the graph. Already do the calculation for you. So yield strength offset 2%, direct. Read from the graph lah. This one you don't need, not even need to do anything. Just in your answer, you just highlight this point, then write this answer. Okay, the question already give you, the graph already give you the value. Maximum load contained by the specimen having original diameter 12.8 mm. So just now you have E 100 Pascal. With diameter 12.8 mm. So here, basically ask you to calculate area and then write the Hooke's law, stress equal to E, strain, stress F divided by A equal to modulus Young that you just find 100 gigapascal. What else? Strain you don't have. But anyway, just now you have one equation. This one you use tensile strength from the graph. So graph gives you tensile strength 450. So link this value with the maximum load. So tensile strength is actually stress max equal to force divided by area. So you're given the tensile strength of 450 megapascal. You have the area by calculating from the diameter. Area equal to pi r square or pi d square over 4. Press calculator, you find the force. Okay. So this basically you rearrange the stress formula. Force equal to stress multiplied by area. So it's still testing you the Hooke's law, the definition of stress, the definition of strain, and so on. Okay, D. Change its length specimen 250 mm. Was tensile stress. Now you change the stress already. And it's tensile means it's pulling both ends. Tensile stress given. So you are given this tensile stress. So basically you are given graph. You not even need formula also. You are given 345 megapascal. So read from graph. 345 is around point A. Mark here, you write 345. Extend to touch the line. Extend down, you get one value. Because inside here, maximum is 250. So you cannot use inside graph. You can use A. So you go to 345, use the graph and extend down. Okay, you get some value, cannot less than 0.05, is about 0.6 or 0.7, maybe 0.7, right? So you know that strain equal to the deformation ratio, right? So here we are use the value from here 0.06. So you put inside here 0.06. Original length is given 250 and one unknown. So you solve the missing parameter. The final answer unit can be meter. If you put in mm also correct. Okay. Any question on the graph? Can So if you're given graph, most of the time you need to give graph rather than using formula. Formula just a support of your answer. Okay. Next is from the graph, then you tell me what the behavior of the material. So here, it just give you stress and strain and the many type of material. So you have magnesium, you have many type of the stainless steels. Okay, so from the graph, what is the strongest material? What is the strongest material? Got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Ah, 11. What is the strongest material and what is the value of the, and justify your answer, why is the strongest from this graph? Ibrahim, what is the strongest material? Huh? What is the material? There's no 240 in the material list. SAE 1340. Why? What stresses? Huh? You? Why you look at you? I ask you the strongest. Why you use U value? The answer is correct. The name is SAE 1340 steel, but the reason is wrong. If you use U, then it's wrong. You should use what? What value? What value should you use? On the whiteboard there, I write something. You should use ultimate tensile strength. I ask you the strongest. Strong means you link with strength. So you use that ultimate tensile strength. It's not 240, but it's above 240. It's about 245 or 246. So if your answer, you give me 240, reason is wrong, name of the material correct. So it's, let's say it's 3 points, you only get 1 point for the marks, for the name, but reason wrong. No marks for the reason. Okay. Now, what is the comparison with maybe, okay, what can you tell me the behavior of nickel alloy compared to the rest? What can you tell me the properties? Anything you describe one properties of nickel alloy compared to other steel? By using these two words, you tell me, brittle and ductile. Elaborate the answer using these two words. What can you tell me about nickel alloy compared to other stand materials by using this graph? Tech G, JYH is what? G. Okay, Tech G. What is what is your answer if this question come up? What can you tell me about nickel alloy? Why? Why it's not ductile? You take one material to compare if you want to use the brittle and ductile. You can take any from here. Let's say you compare with SAE 1340. You see, almost same value with the UTS, with the SAE 1340, but the curve is different. What about the elastic value? Which one is lower? Which one more steeper? You see nickel is here and here. So it's about this graph. So you have two lines. One is steeper, one is like that. So you have M1, M2, or E1, E2. Which give you lower value of modulus Young? E2. So you can say nickel alloy is what? Is more what? More what compared to SAE 1340? More brittle or more ductile? More brittle. This one you need to check. What is E? E is stress divided by strain. Let's say you fix your stress 100. E is changing, right? So material 1, E1 is more steeper, right? So more steeper, it means what? Your E value is bigger or smaller? Smaller, ma. So what I mean by smaller E? This is deformation. So this one smaller, it gives you higher E, but higher E also means something. If you compare apple to apple, you maintain your stress and you look at the strain. So if M1 or E1, like for example, in this case, SAE 1340 have a higher E. Higher E means smaller value of elongation ratio. So it means it's more harder to change length if you pull. It means more brittle or less ductile compared to nickel alloy steel one. Because alloy steel one you have more easier to pull nickel alloy because because of the strain value inside here from the Hooke's law. Okay. Then nickel alloy also nickel alloy steel one also failed earlier compared to SAE 1340. It failed more early because the point stopped here. Okay. SAE 1340 is still able to sustain longer elongation before it snaps or fail compared to nickel. Okay. Okay, among these 7, which one is the most ductile material? Ductile means you can pull until it cannot break on until one point, then it only snaps. Which one? Which one can hold the longest elongation? It can be structural steel, it can be N155, either these two. But what is the difference between these two? The stress point. The stress point will be different, although the strain is almost same. So means that one N155 can handle higher strength or higher value of stress, but structural steel will snap on cannot handle more than maybe 50 or 40, maybe 50 50, more than 50 value lah. Here is in PSI. So it is the stress is lower compared to N155. Okay. So this is how you tell the behavior of the material lah. Okay, important you understand the gradient, the E, the strain, this one. It's important, Okay. The rest you read lah. Okay. The previous chapter we introduced you the engineering stress. There's one more value is called true stress. So that the area doesn't change as we do the calculation. Because the force, when you apply, the area in our calculation stress here, we assume is continue to maintain the diameter. So in the real case, it's not so. Cross-section area will change as you do your tensile test. So the engineering stress calculated will not precise if you maintain your area. Actually, it's changing all the time. So there is this one you need to get from experiment, the blue line or the purple line. You need to get from experiment. Okay. So it just tell you that there's a true and strain. So there's a calculation there. So how do you calculate? Because this is a curve. So you true strain. Oh no. Okay. The rest you read, Okay. True stress is get the average force divided by instantaneous cross-section at that point. True stress, you can only look at that particular point. For example, this point is different from this point and this point and this point. So you need to get area of that particular time. Instantaneous means you stop the time and then you see what is the true force at that. So true stress is actually changing all the time. It depends on what point you want to focus on. However, for the true strain is an integration of the strain, the changes of strain. So true strain equal to original length to the instantaneous length that you want, and it's a dl over L. Okay, dl over L. So if you do the operation of integration, 1 over L is ln. So ln L I over LO. Okay, this is integration operation. Okay, if you integrate LO, L, Li, 1 over L, dl. So this one become ln L and Li, LO. So you substitute inside there. Okay. LDL. LDL means you add in L here. Or maybe I should put the capital L here. So when you do ln, it become ln L over L. Like that. Then you substitute your L there. LO is gauge length. Li is instantaneous gauge length. So in the tensile machine, this one already programmed in the machine. So if we assume in our calculation by looking at true strength, if we assume that we have constant volume of a gauge length section, I mean if we test this subject, we assume that the volume doesn't change, right? No matter how much you pull, the volume of this cross section will be the same no matter where you pull. So you write LO A, LO multiplied by A, you get volume. LO is before, LI at that time of experiment. So L multiplied by A, you get volume. Then you shift them. So you pull Li to the left, you get Li divided by O. Pull your AO to the right, you get AI. Wrong already. Correct lah. You pull your LO to the right, pull your AI to the left, you get the second equation on the screen. Then you pull this equation inside the Lon equation. True strain also can calculate using length and area. It's the same. Huh? This equation apply only true only when we assume there's no changes of volume in the test section. Okay. Okay, this one is for your reading. Most of the time I won't ask you true stress things, but it's good to expose to you that actually you need to consider true stress in your application. So there's a conversion equation. Engineering stress to the true stress. So true stress equal to stress. This is engineering stress bracket 1 plus strain. This is a equation to link true stress and the normal stress or engineering stress and the engineering strain. This one is conversion of true strain linked with the engineering strain. So engineering strain, true strain equal to ln bracket 1 plus E. So on the left is to calculate stress, on the right is to calculate strain. Okay. I'll let you know if this kind of question come up. If the question asks you true stress, true strain, then these two equations are expected. So it will previous calculation that you calculate engineering stress and strain, then you use this equation to find the true value. Okay, this is just an add-on. Is no whether you know or do not know lah. Okay, this is just an illustration of necking behavior. So if you calculate previously, we have stress, engineering stress equal to modulus Young strain. So if you're looking in the dimension of true stress and true strain, you need to use this equation. True stress equal to K modulus Young exponential n of your strain, true strain. K and N, they are constant that you determine through experiment. Okay. Okay. So the N is called strain hardening exponent. Less than unity means less than 1. You're less than 1. Finding the N alone can be a master program or PhD program alone. You can get one PhD by finding the N alone. Okay. Okay, these are the chart. If you see this chart or this table with the N and the K, means it forces you to use this equation already. Okay, true stress equal to K strain through N. So you have a K and N. You can find the true strain, true stress by using different material over here. Okay. Okay, we'll go a little bit more. Compare engineering stress and strain with the true test through test and strain for the tensile stress low carbon steel with the following amount. So you are given Newton load, initial specimen in 12.7 mm or half inch. Diameter specimen under this loading will be this one. Compare the engineering stress. So you calculate the engineering stress first. Engineering stress equal to force divided by area. So engineering stress, you take this value 75620 Newton divided by area pi d square over 4 or pi r square divided by 4. This is diameter. So I saw some careless mistakes here also in the previous test and final exam. We give you diameter. The student use pi r square. You will square the diameter. Careless mistakes. So to solve this kind of question, always write a general equation. You write stress equal to force divided by area. Then you get one value. Find the strain. Strain you don't know because you only have initial diameter. So area, you find area under load. Oh, that two. Diameter specimen under load is this one. Initial diameter. Oh, so you have two. Then you can find the changes of area. So area, before start, you use this one. After start, you get this one. So area string. Area string a little bit. So assume, you write this one, assume no volume change. This one, because the question already give you compared to the true value. So you need this statement. You write no changes of volume. LA before equal to LA after. Then you get the ratio. Normal stress, substitute value. You get one value. Engineering stress equal to 596.94 megapascal. So strain equal to a ratio of deformation. Ratio of deformation, you take final divided by changes of length divided by total length. Okay. So you can take as a area also. Okay, changes of area. This one is actually another presentation of mathematics. It's actually you take initial area and in so you get 1 minus 1 there. Okay. So you get 0.12 for the strain. Strain, it can be length, it can be area. Length can be area. Once you get these two numbers, you have area, you calculate area, area under load, calculate stress, calculate strain. This one, 4 marks here, already 4 marks here. Then you put in the calculation. True stress is force divided by that particular time. So instantaneous area, you calculate already, substitute, you get that one. Strain also same. You use the ln area to calculate is 0.15. 0.15. Okay, so this is how you find. Okay, so this one can combine with the previous example. Previous example is more on the engineering stress, normal stress, and then the question can extend to compare the engineering stress with the true stress. Okay, usually you see the word compare, you need to calculate the percentage of differences between the normal and true. Normally, normally. So this step doesn't complete lah. if the question mentioned compare, you need to tell what is the differences between normal and true. Okay, you'll see this one in your coming lab session. It is the hardness. Hardness, how you test the material hardness by pressing the material surface. Okay, we call it indentation. Indentation. So let's say you have a two piece of material. So aluminium and aluminium A, aluminium second formula B. So when you press, it's like you make a hole by using a diamond. Diamond, diamond when you cut, it's like a pyramid shape. This one like pyramid shape, right? Pyramid shape. So like this. So pyramid shape, when you do indentation, what do you see after you indent it? It's like a chop something. So what do you see from the top? You see a square or diamond shape like that, right? You do like that, but there's a depth of the thing inside there. If you draw 3D, there's a depth there, right? So let's say A is A is stronger than B. What is the size of B? I draw something on the whiteboard, right? Will it be bigger or smaller if A is stronger? You do the same, you press the same force, let's say 100 Newton. When you have stronger material, do you see the same size? It should be what? Smaller, because it's more harder to penetrate. It's more harder to squeeze the material out. So you'll get a smaller shape, and also the depth also different. So in your instrument, in this instrument, different shape of prism or parallelogram. How you measure is measured by only two parameters you can measure: horizontal distance and vertical distance. Okay, you can only measure here and here. Then you compare side by side. There's a formula. You compare. There's a value of hardness. Okay. So this is the diagram of the indenter. So indenter go down. You apply load, then it will stay there for 5 seconds, 3 seconds. This one you can set by different standard lah. So normally what you do, you place the spaceman, then you press the indenter or hardness test. It will go down, press, stay there for 2 seconds, 3 seconds. Then you will come out. Why you need 2 seconds, 3 seconds? Just to make sure that you apply the load to all the surface. Then you let go. You have a thickness, not thickness, the depth here, the T there. So you are using different formula using this chart. How you separate? If the indenter is round shape, it's like a Doraemon hand, round one, right? So you press, you'll see what? You'll see a sphere shape on the surface. You press with a round object, you'll see round things. So if you're using indenter, round indenter, the test is called Brinell. The formula is using this one. Okay, so this one you don't need to memorize. If this test come up, this diagram, the correct shape of the indenter. So this one, Brinell hardness BHN means Brinell hardness value. 2P, what is P? P is the pressure, load. means Newton in Newton. Load 2P, let's say P is 100 Newton. So on the top is 2 multiplied by 100 Newton. Pi D, D is what D? D is this one. D is the indenter D, the indenter, sorry, indentation, side view. This one usually is the indenter things. Okay, the indenter, side view. Okay, then you apply what you see on the object, the D, the small d here, you substitute inside, you get one value. If the indenter is pyramid shape, this is what we have in the lab. So when you have an indenter or pyramid, we call it viscous test. So you'll see a square shape or diamond shape. You measure the D1 and D2. Usually the same material, you will see the same D1 and D2. Almost same almost same. So the machine will measure 2 times D1 and D2, the diagonal distance. Then you apply vernier VNH, viscous hardness value. You use 127 P divided by the D1 multiplied by D2. In experiment, you need to measure 2 times. You just press on the machine. This one. Because the microscope, you can still see the indentation, but you cannot measure the things, right? And if you have another type of diamond pyramid, we call it note. Also, you follow the formula. Rockwell is a cone-shaped indenter. Cone-shaped. So when you press, you're still seeing a circle because it's cone. So it depends on A, B, C, D indenter grade based on the load that you put here. Then you find the thickness of the depth lah. Okay. I think this one is the last example for example 6. Okay, so this is application of what you learned in chapter 6. A tensile test apparatus constructed to withstand a maximum load of 200 to 220 kilonewton. Design call for 2 cylindrical support posts, each wish to support half the maximum load. You need to draw the diagram out to solve this question. This one, testing apparatus construct that can withstand maximum load. Maximum load, you write sigma max 220 kilonewton. Design call for 2 cylindrical support posts. You have 2 legs, call support 1, support 2. Each one support half of the maximum load. Can support max 1, can support 100 kilonewton. Read carefully the question. Further, plain carbon steel ground and polish is used. You are using plain carbon steel 1045. This kind of question, you will see a material table at the back of the question. Minimum yield and strength, this alloy is given. So you are given U. How many? U 310 megapascal. Tensile strength, UTS 565 megapascal. Specific a suitable diameter of the support post. with the safety factor use N5. So safety factor N5, FOS, factor of safety, equal, equal to value of design, value of application divided by value of design. Yeah. Okay, so let's say your FOS is 2. Your design, I just put a lift application. Lift application cable, let's say is 100 Newton, kilonewton. So if you have a FOS of 2, you tell your customer, this only can sustain 50 kilonewton. So if work this, I rewrite this equation. So FOS equal to value of design divided by value where you tell your customers. Okay. So you get the value of FOS. The higher value of FOS is more conservative, is this? Or you might have over-designed the thing because you need more material to sustain the thing. Okay. So the working stress will be U divided by N, or N will be U divided by working things. Okay. Working stress is the one that you tell your customers. Yield is the one that it will fail or start to show plastics. So you take 310 divided by 5 is 62 megapascal. So this one is the working stress. This will be the value of maximum in your design. Okay. So from stress, you work back. Stress equal to force divided by area. The purpose of giving you the N of factor of safety is to reduce the stress value for your design. Okay, that means this is 62 is the maximum value that you can use in your design. You calculate the area. The area is pi r square or pi d square, pi d square over 4. It should be square. Okay, force, then you find the diameter. Okay, you rewrite this equation. Right? The square I should put outside. There's 2 here. I should put outside the bracket. Typo error in my slides. Okay, you rearrange, you substitute value. Force is 110 kilonewton. Pi, the value that you use here, you should use after you consider the safety factor or the value that you tell your customers. Very conservative numbers, right? 62 megapascal. The diameter is 4 point something, right? 4 point something, or 47.5 mm. So this is the thing that you should use. So you should able to read the question carefully. If you use 220 over here, it will be wrong. because the question trick you it give you extra information of 2 and make you confused. They actually ask you to calculate 1 for the one support. Design call for 2 cylindrical support, each of which to support half the maximum load. Okay, so it asks you specify a suitable diameter of this support post. It asks you individual posts. Okay, so just be careful when you read lah. Yeah. Yes, yes. So it already give you the value already. It already give you the value here. If this value not given, then you need to read from table. Okay. So with this, we conclude chapter 6. With this, we conclude chapter 6. Okay. Any question? There are only a few formula for this chapter 6. It's only applying. When you apply, just need to be careful what the question want you to calculate.